Hello, everyone. I'm Fiodar, and today I'll be talking with Deepak about POP, a method to efficiently solve large-scale resource allocation problems. This is joint work with collaborators at Stanford and Microsoft Research. So as everyone knows, computer systems are becoming larger and more complex. We see modern clusters with thousands to tens of thousands of workers. Another example is wide area networks, which are growing and have many nodes and edges. As these systems become larger and more expensive to maintain, it has become essential to share them among many users or clients to amortize costs. As a result, the way resources in these systems are allocated among users has become increasingly important. We have resource managers that allocate system resources, for example, servers in a data center, to clients or users of the system, with an objective in mind, whether it's fairness among clients or maximizing the global utilization of the system. And it outputs an allocation, which maps clients to resources in the system. This abstraction applies not just to cluster scheduling, but to other systems as well. Clients can be commodities in a network, where we allocate link bandwidth in order to maximize the total amount of flow. The allocation might be recomputed every few seconds or every hour, depending on the temporal properties of the clients using the system. As a concrete example of resource allocation problems, let's consider the assignment of servers to users with a simple utility maximization objective. Utility in this case encodes the preference of user I to server J. An example could be the cost to run the job on a particular cloud instance. This resource allocation problem can be formulated as an integer linear program, shown here on the left, and we approach it in a couple of different ways. For example, we could directly use a modern state-of-the-art solver like Mosaic, and this would take a long time to run, several hours for a system with thousands of users and resources. Or we could devise a heuristic, such as a greedy algorithm, to try and solve this problem. This could do okay, but might also get stuck in a local maximum and never find the true optimal solution. We can put both of these approaches on a runtime versus allocation quality graph. Ideally, we want to live in the top left corner, where we can compute the best possible allocations extremely quickly. Heuristic algorithms typically live on the bottom left of this graph, fast but often producing low quality allocations. Mathematical program solvers can compute optimal solutions, but scale poorly, occasionally with exponential worst-case runtimes. This is too slow to be deployed in large systems. And the trade-off between these two approaches is quite severe. The difference in runtime can be several orders of magnitude, and heuristics can be far from optimal. In this talk, we propose a new technique called partitioned optimization problems, or POP. We identified a class of resource allocation problems, which we call granular, and found that many optimization problems in existing systems belong to this class. We can solve granular problems quickly with POP. A distinguishing feature of POP is its simplicity. We take the system and its mathematical problem formulation, randomly partition it, solve the optimization problem on each partition, then coalesce the results into our final allocation. We'll also show how problems that are not granular can be easily transformed into granular problems, on which POP can be applied. In general, we find POP can produce higher quality allocations compared to existing heuristics, and much faster compared to using solvers for the full problem formulations. It's also incredibly easy to implement. It applies to a wide range of systems as well as allocation objectives. We tested POP on many different objectives and systems, including job scheduling and server clusters, traffic engineering in wide area networks, and load balancing in distributed databases. Empirically, we see up to several orders of magnitude faster runtime, while computing allocations that are within 5% of optimal, and up to 1.9 times better when compared to heuristics. The rest of this talk is organized as follows. We first characterize a class of optimization problems that occur in large systems, We then describe how to pop these granular problems and evaluate on several different systems and objectives. Our key insight is that a number of allocation problems across domains, such as cluster scheduling, traffic engineering, load balancing in databases, these have several properties in common. The first is scale. Systems can have hundreds or even hundreds of thousands of clients and resources. This is partly what makes these problems hard in the first place. The second is that clients are small. This often goes hand in hand with scale, and each client can use only a small fraction of the available resources. The third condition is fungibility. For every client, there are many resource instances on which they get similar utility. For example, a GPU cluster will have many identical GPUs, and a client doesn't prefer one over another. Our technique, POP, exploits these conditions to quickly compute good allocations. Let's look at examples of granular problems. In real systems, the server assignment problem I mentioned earlier is granular. When the system is large, there are many users and servers. Each user requests a small fraction of available servers, and we typically see many instances of each server architecture in the resource pool. Here's a more complex example from a research system published in 2020, featuring a GPU cluster with several types of GPUs. The allocation objective is standard max-min fairness. Maximize the minimum normalized throughput of any job in the cluster. What we want to compute is an allocation matrix A, where AJI specifies the fraction of time a job J spends on resource I. There are also constraints that ensure that this matrix represents a feasible allocation. So no job gets more resources that it can use, and no resource is oversubscribed. In large GPU clusters, this problem is granular. We have large numbers of jobs, no job is too big, and there's a large amount of each GPU type. Next, Deepak will describe how POP operates on these granular problems.
Thanks, Fiodar. I will illustrate how the POP method works for the server assignment problem from before, at the level of both the system and the optimization problem. With POP, we start with a large system with n clients and m resources and split them into k subsystems, where each subsystem has an equal share of clients and resources. Remember that our original formulation modeled the allocation as an n by m matrix of variables. With POP, instead, each subproblem is now responsible for only a subset of the clients and servers in the original problem. In our particular example, each subproblem has a smaller allocation matrix of size n by k times m by k. POP is able to achieve runtime speedups over the full problem formulation since the runtime of solvers scales super linearly with the number of problem variables, and subproblems can even be solved in parallel. The main reason we can only apply POP to granular problems is because our method reduces the search space that solvers consider. We need granularity to ensure that the solver is able to consider enough high-quality feasible allocations. For example, client resource fungibility ensures that every client has at least some resource that it has high affinity towards in the same subproblem. Thus, to recap, using POP for this server assignment problem is simple and consists of 3 steps. First, we randomly partition users and servers into subproblems. Then we use the original solver and problem formulation for each subproblem, and then we concatenate the resulting allocations. We can do something very similar for the fare sharing policies used in Gavel from OSTI 2020. Not all resource allocation problems, however, are granular. It is easy to imagine clients with large demands which violate condition 2 of granularity. Similarly, many systems can also have rare or unique resources, violating the fungibility condition or condition 3. One specific class of problems where these violations can manifest themselves is in traffic engineering, where every link between two sites is a unique resource. Specifically, let us consider a simple max flow traffic engineering problem, where we try to allocate link capacity to various commodities while respecting and trying to get as close to each commodity's demand. This problem can have commodities with high demands and might also require the use of links between specific sites to ensure high total flow. In such cases, we can apply client and resource splitting transformations to transform such non-granular problems into granular ones. To deal with clients with large resource demands, we use a procedure that we call client splitting. At a high level, with client splitting, we take large clients, for example, commodities with large demands, and split them into many virtual clients. These virtual clients are then distributed across subproblems. Allocations for all virtual clients corresponding to the same real client then need to be aggregated across subproblems. In this work, we show that greedily splitting the largest clients works well in practice. A client splitting algorithm is problem agnostic, and for more details, see our paper. To deal with the problem of unique resources, we use a procedure that we call resource splitting. Let us consider again a traffic engineering problem where each link is a distinct resource with some capacity. One way to partition this network over many subproblems is to split it by nodes. So some nodes go into one subproblem and others into a different subproblem. Edges can be similarly partitioned. This, however, can lead to suboptimal total flow outcomes since the solver now cannot use certain edges since they are no longer a part of the input to the relevant subproblem. Concretely, for this example, we cannot use edge E when trying to allocate link capacity for a commodity between sites A and B. Instead, we can create copies of the network where each subnetwork has all the links, but with a fraction of the original capacity. Now, whichever subproblem has the commodity between sites A and B can use this edge E to maximize total flow if needed. By applying these transformations, we can thus make the original traffic engineering problem granular. This problem now satisfies the conditions of granularity from before. Large problems have thousands of commodities and resources. And by splitting commodities with large demands into smaller virtual clients, each client in the POP problem requires a small fraction of the total resource pool. Additionally, with resource splitting, client resource fungibility is now also respected, since each client has multiple copies of the same link to choose from, and each client has equal preferences for each of these copies. Let's now see how POP does in practice. We evaluated POP on 3 different domains: DNN cluster scheduling using the problem formulations from the Gavel research system, which appeared at OSTI last year; traffic engineering using the problem formulations from the NC-Flow research system, which appeared at NSTI earlier this year; and load balancing for a distributed database using a formulation similar to the one used in the eStore research system, which appeared at VLDB. To evaluate POP's generalizability, we tested it on different objectives. For example, for the cluster scheduling domain, we looked at 3 different objectives: maximum fairness, proportional fairness, and minimize makespan. For the traffic engineering domain, we looked at 2 objectives: total flow and maximum concurrent flow. The evaluation section in our paper also has various micro benchmarks evaluating the effectiveness of client and resource splitting, as well as overall partitioning strategy. For reasons of time, I'm only going to discuss a subset of these results in this talk. Our method shows extremely good results in practice. For example, with the maximum fairness objective for GPU cluster scheduling, we can produce up to a 23x speedup in runtime with little drop in accuracy compared to using the full problem formulation. Note that POP-K uses K subproblems, and the speedup increases as the number of subproblems increases. The x-axis in this graph is logarithmic scale. We can also improve allocation quality by up to 1.9x compared to heuristics like those employed by the Gandiva scheduler. These results are for a static workload, but we saw similar order of magnitude speedups when using POP with Gavel's simulator, with little change in relevant end-to-end metrics like average job completion time. POP also does well for various traffic engineering objectives. Again, the graph here is with a logarithmic scale on the x-axis. For the total flow objective on a topology with 754 nodes and 1790 edges and 500,000 commodities, we see that POP with 64 subproblems is up to 131x faster than the original formulation, while returning 99.9% of the total optimal flow. Runtimes can decrease from hundreds of seconds to about a second, making it practical to keep using optimization problem formulations for these resource allocation problems. We can also apply POP to maximum concurrent flow, which is a fairness objective for traffic engineering. POP can decrease runtimes here from hours to tens of seconds with minimal impact on the total allocation quality. Thus, we see that POP is able to accomplish faster runtimes with almost identical allocation quality across different objectives. We also validated POP's speedups on real-world traffic matrices. This experiment was run for a total flow objective on real-world traffic matrices on a private wide area network topology. We used POP with and without client splitting and also compared POP to NC flow, which is a state-of-the-art approach recently proposed at NSTI that is explicitly tuned for total flow. We showed two graphs here. The graph on the top shows total flow relative to the original problem formulation, and the graph on the bottom shows speed up relative to the original formulation. We have two main takeaways from this experiment on real data. The first is that client splitting is necessary in order to realize gains from POP. And the second is that we can accomplish speedups of about 12.5x compared to using the full problem formulation, as well as competitive performance to the tuned NC flow approach. To summarize, POP has many benefits that make it an attractive technique to accelerate resource allocation computation in computer systems. First, it's extremely simple and avoids the need to design new heuristics from scratch to scale up to larger problem sizes. Instead, the original problem formulations can be reused. Second, the same POP approach works well for a number of different objectives, such as total flow and maximum concurrent flow. Third, POP is tunable. The number of subproblems is a knob that helps us trade off between allocation quality and runtime speedup. And finally, POP is able to accomplish strong empirical results with order of magnitude speedups with little to no drop in allocation quality. To conclude, in this work, we made the observation that many real allocation problems are granular and can be accelerated using a method we call POP. POP uses simple random partitioning into subproblems and simple greedy client and resource splitting algorithms that work extremely well in practice. And our key takeaway is that one shouldn't give up on large problem optimization problems or fall back to heuristics for resource allocation. Instead, POP provides an attractive alternative. Our code is open source at this GitHub URL. Thanks for listening.